So this next topic is kind of a small topic, but it leads into a lot of bigger things later in the semester. Um, I mean, for example, have you ever wondered like why when you wax your car, the water beats up on the car, or maybe like why when you add soap or detergent to water, it seems to stick to the clothes better or lift the grease out and things like that. And it turns out all those phenomena are related together to one thing, okay? And it has to do with what's called molecular polarity. So, you think about the Earth. The Earth has, right? It's this shape, and it's got a north and a south. It doesn't really stick straight up like that, but just most people's conception of it's kind of like that. And so what do we call these things? Like, where does Santa live? Right? He lives in the North Pole, if you believe in Santa. Sorry. Just have to laugh at why I'm saying it's Santa Claus. But anyways, yeah, we have poles. We have the North Pole and the South Pole. So that's what we call poles, right? And so when we're talking about polarity, we're talking about molecules having poles, but the poles are not magnetic poles. They're actually charged. So they're like plus and minus. So it turns out molecules can have polarity. And that's what we'll explain in this section. So here's the first thing you have to do. If you want to know whether or not a molecule is going to be polar, the first thing you have to do is you have to figure out or whether or not the bonds that are between the atoms are polar. Okay, so if those aren't polar, it turns out the molecule won't be polar. What we use to make that assessment is electronegativity. Okay, now, I'm not going to spend a lot of time explaining electronegativity, but the basic definition is this. It's the attraction of an atom for electrons in a bond. So think about HCl. And HCl, right, that's hydrochloric acid. So that's a molecule with just one bond in it, so it's easy to analyze. I have hydrogen over here, and I have a chlorine over here like this. Now, when I look at the electronegativity, chlorine's electronegativity is a lot higher than hydrogen's. It looks like these are the numbers. Now, I'll show you where you get those. But basically everything we do in this class is not based on the numbers. You do a lot of initial stuff with the numbers to determine whether or not a bond is polar or nonpolar, but for the most part people just look at the periodic table, and that gives us a pretty good indication of whether or not it's polar or nonpolar. So if and this is the Lewis structure like this, okay? Now, if the electronegativity was the same for hydrogen and chlorine, that is, that they had the same attraction for the electrons in the bond, because they have a single bond in between them, so I'm going to draw it like this. The electrons would be there. This would be equal electronegativity, and I'm just going to do E subscript N for that. So that's what this is here, right? Okay, but it's not the same, right? You can get it to be the same for, like, example H2 or N2 or F2 or anything like that. Any diatomic, those are always exactly the same. Or two carbon atoms bonded together, those would be exactly the same. But H and Cl have very different electronegativities, and chlorine being on the right-hand side of the periodic table, turns out generally things on the far right have higher electronegativities. And so we know that the electrons actually don't distribute that way. They distribute like this. So they're going to be closer, even though, when we draw that bond as a line, we just draw it as an even line, really the electrons, the ones they're sharing, are not equally shared. The pair of electrons in that bond are closer to the chlorine, I drew carbon, let me rewrite that, are closer to the chlorine than they are to the hydrogen. So what that does is it unbalances the charge. So remember, hydrogen is used to having one electron. He kind of partially took that electron away when chlorine was allowed to take it, right? So what that means is the chlorine side is going to be a little bit negative, and the hydrogen side is going to be a little bit positive. But it's not a full plus, it's not a full minus, because they're still kind of sharing. Like they have the candy bar, but chlorine ate 2/3 of it, okay? And so this is going to be partial positive. That this I'll draw it really big. That's a delta. It's a lowercase Greek letter D, and so uppercase is usually meant to be like a full difference, but this is a partial difference in charge. So we'll do it like that. We could also draw it like this, with a cross on this side. So this indicates the direction the electrons moved and which side is positive at the same time. So this hydrogen chloride, right, HCl, with the hydrogen's electronegativity being lower and chlorine's electronegativity being higher, the electrons are closer to the chlorine side. And we would say that HCl as a molecule is polar. This bond is polar, but the molecule as a whole is polar because the electrons are really drawn off to one side of the molecule. So HCl is a polar molecule. And it's polar because the electrons in the bonds aren't evenly distributed. I'm going to say this, they're unequally shared. That's usually the way you hear it. Like that. So it's the electronegativity difference that we look at to figure out whether or not bonds are polar. Like I said, for the most part, you do some of the calculations, and you'll definitely be required to do some calculations. I'll give you some of the numbers. But basically, all you do is you subtract the numbers. So like the electronegativity difference for HCl would just be 3.5 minus 2.1, so that ends up being 1.4, like that. So that difference is what we look at to determine whether or not something is polar. Now, there's a scale that we use, right? And I'm going to draw it like this. This is a number line, right? I'll put 1 here. I'll put 2 here. And then I'm going to mark out 0.4, and this is an important value. Let's see, 0.5 would be here, so 0.4 would be about here. So this would be 0.4. And another one that I'll mark that's important in your book in any case is 1.7. I didn't put the 1 in the middle. Oh well, we'll live. This is about 1.7. So these are sort of landmarks that are important to remember, okay? Now, if you are in this range, below or equal to 0.4, so including that line, this is non-polar. That means even though they're not completely equally shared, there's not enough movement of the electrons in the bond to make one side really more positive than the other, okay? Now, anything beyond there would be polar. So for example, let's do this. From here to here, right? Anything above 1.4 all the way up to 1.7 would be considered to be polar. Oops, I thought I hit the pen. Let me do that again. Here, let's do this. Hang on. I just wanted to erase that bit. Okay. And that bit. This is going to be polar. And oftentimes in describing those bonds, we would say they're polar covalent. And actually, non-polar is normally called covalent, just pure covalent. So there's covalent, that's shared, but there's purely covalent, which is non-polar, and then there's polar covalent, which is shared, but it's like HCl, chlorine ate 2/3 of the candy bar, hydrogen only got 1/3. He's a little bit positive, and I was going to say she, but there's no reason it has to be a she. CL is a little bit negative. I think it was just the sounds in my head that made me say H, because he and she, CL. Anyways. All right, so above 1.7, these are going to be ionic. So this goes on a little ways, not too much further. And the guy who came up with this idea, so over here we call these ionic. So ionic bonds, like we talked about in the very beginning, completely not shared. One atom just takes the electrons from the other. So this scale was originally come up with by a guy named Linus Pauling. So this often you refer to this as the Pauling electronegativity scale. So these are Pauling values. And generally speaking, this kind of scale that we draw is what people use. So, for example, HCl at 1.4 falls over here. Right about there. And so that's why we would say, oh yeah, it's the bond for HCl is polar, and because there's only one bond, the molecule has to be polar as well. All right, so how do you know when a molecule's polar? Now, people will try to, like you on YouTube, or you go to other classes, they try to make you like see 3 dimensions, right? And to start with, you're looking at a 2-dimensional screen right now, and anything I draw is 2-dimensional, right? So you do kind of need to see in 3 dimensions, and you do, right? You see in 3 dimensions, but you do actually have to be able to visualize in your head, see that way in 3 dimensions in order to sort of really figure this out. But let me show you the simple way to do it, right? So if it has a molecule will be polar if it has polar bonds, right? And it's not symmetric, or the other way to say it is if the polar bonds are asymmetric. So if it looks like this, that has symmetry to it. But if it looks like that, and I ate the other cherry. If there's a cherry here, it's asymmetric because the 2 bonds, right, are one side of the molecule. This is also symmetric because I have the 1 in the middle, right? But they're evenly distributed around. As soon as I put a lone pair on it, or 2 lone pairs on it, it becomes asymmetric. So really the trick, okay, you know how to determine whether or not a bond is polar, and we'll practice that a little bit, but you know how to tell if a bond is polar because you look at the electronegativities and you subtract, and you can tell that way. You can also basically look at the periodic table, and we'll do that in a little bit, and tell whether or not it's going to be polar or not. But the hard part really is to tell whether or not the molecule is polar. And it basically boils down to this for what we're doing. 1, not all the atoms, not all the atoms that's one way you can tell. So if you have like 3 atoms around a central atom and not all of them are the same, or 4 and not all of them are the same, and again, remember, with no lone pairs, then it's probably polar if the bonds are polar. Second thing you can look for is you can look for one of any atom. All right, mic went off. Typically what we see in like a Chem 3A class, one of any atom, any high electronegativity atom. But typically for a 3A class, it's oxygen or chlorine or fluorine. O, F, or Cl. Those are dead giveaways. Like if you have one of those, that molecule's polar. You don't even have to look at everything else, to be honest with you. And the other way to tell is, the third way to tell is it has lone pairs. So it's got to have polar bonds, but you can tell it's asymmetric if not all the atoms are the same. You have one of any high electronegativity atom, that's usually a dead giveaway, or you have any lone pairs, and you have polar bonds, and then the molecule is going to be polar. And then it will do like all those things, like bead up on the wax, fresh wax of a car, or it'll make clothes have static cling to it. It's all kinds of stuff like that this phenomena is related to. That's kind of it for this chapter. And the next chapter, if you actually made it all the way to this point of the videos, congratulations. The next chapter will be chapter 15. Okay, so we're going to do them out of order, but chapter 15 sets up a foundation for 11, 12, 13, and 14. So I like to put it first. I don't know why they put it last. anyways, that's it. If you have any questions, again, feel free to contact me.